Hello, today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on thermal physics. First, let's just work through the formulae and other information that you're likely to need. The ideal gas law, PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the molar gas constant, and T is the temperature. Bearing in mind very few gases are ideal gases, but some at least behave close to an ideal gas to enable us to use the formulae. R, the molar gas constant, has a value of 8.31 joules per mole per Kelvin. The Avogadro number, or Avogadro constant, is 6.02 times 10 to the 23 molecules per mole. So in any mole of a substance there will be 6.02 times 10 to the 23 molecules. Kinetic energy of a gas, which of course we could typically write as a half mv squared, where v in this case is the average velocity of the molecules in a gas, given that they will all be travelling at different velocities. But if v is the average velocity, then that equates to 3/2 times kt, where K is the Boltzmann constant and T is the temperature. The value of K is 1.38 times 10 to the minus 23 joules per molecule per Kelvin. And that means that the gas constant, R, is equal to the Avogadro constant times the Boltzmann constant. Then we come to the formula E equals kT. Now it's here that people often ask me, what is the difference between E equals kT and E equals 3/2 kT? Well, in the case of E equals 3/2 kT, this is a formula that is derived from the ideal gas law, and considering molecules moving about in all directions, you work out what proportion are hitting the walls of a cube, a theoretical cube, and you calculate the pressure, which results from the force over the area, and from that you can work out that the average kinetic energy, which is associated with the average velocity, is 3/2 kT. The formula E equals kT is a measure of thermal energy. The previous one was kinetic energy. Now they are not exclusive, of course. Kinetic energy can include thermal energy and vice versa. But this is specifically a thermal energy measure. It is the average thermal energy of a particle in a system, and it is derived from the Boltzmann statistical distribution. So if you are asked to find the average kinetic energy or velocity of a molecule in a gas, then you'll use the kinetic energy equals 3/2 kT. If on the other hand you're asked to find the average thermal energy of, say, a molecule in water, then you'll use E equals kT. E equals kT is not precise, but it is near enough. Next, there are two equations to do with specific heat. If you take a mass of a substance and you raise it through several degrees Kelvin or centigrade, then the energy required to raise the temperature will be the mass of material multiplied by its specific heat multiplied by the change in temperature. If you are changing the state of that material, for example, you're taking a solid and converting it to a liquid, or taking a liquid and converting it to a gas, that's called changing state, then the energy required to either vaporize, that's to change it from liquid to gas, or to melt it, to change it from solid to liquid, will be the mass of that material multiplied by the specific heat associated with vaporization or melting. Next comes the first law of thermodynamics, delta U equals delta Q plus delta W. That means that the change in internal energy of a system is equal to the heat in plus the work in. The key here is to keep your signs the same. The energy of a system increases, and it increases by the amount of delta Q, which is heat in, plus delta W, work in. If you're taking heat out, or if you're getting work out, then you have to change the sign, it becomes negative. And remember two terms that may be used in association with questions on this. The terms are adiabatic and isothermal. Adiabatic means that no heat goes in and no heat comes out, which means, of course, that delta Q is 0. Isothermal means that the temperature remains unchanged. And if there is no change in temperature, then there will be no change in delta U. Delta U will be 0 if the temperature is constant, because internal thermal energy is a function of temperature. Finally, if you're told that the system remains at constant volume, then no work will be done. Delta W will equal 0 because you only get work in or out if there is a change in volume. And then you may need to know the Boltzmann factor, which is E to the minus epsilon over kT. This is usually associated with activation energies. If you need a certain energy in order for some kind of process, maybe a chemical process, to take place, that energy that you need is epsilon. K is the Boltzmann constant and T is the temperature. The Boltzmann factor tells you the proportion of molecules which will have at least the energy epsilon depending on the temperature T. Then this graph shows the distribution of molecules. We have the number of molecules plotted against the energy. You'll notice that the average energy is kT, that's where we get E equals kT from. But you will see that there are some molecules that will have a very low energy. Some molecules will have a very high energy. So if there is an activation energy that is, say, at this level, then there will still be some molecules in the distribution that will have more than that activation energy, and so the reaction will take place. The extent to which it takes place, of course, depends on the proportion which has that energy or more. And the final graph is a graph which plots the Boltzmann constant against the temperature, and essentially that Boltzmann constant is measuring the proportion of the molecules which will have the energy epsilon. If T is 0, then none of the molecules will have the energy epsilon. If the temperature is extremely high, then they will all have the energy. If epsilon equals kT, then essentially the proportion will be 1 over E, which is 0.37 or 37%. Question 1. The mass of a mole of nitrogen is 0.028 kilograms. A flask contains 0.032 kilograms. How many moles are there? Well, this is very easy. You just take the mass of the nitrogen, which is 0.032, and divide it by the mass per mole, which is 0.028, and that will give you 1.14 moles. Part 2 of the question, if the volume of the gas is 0.02 meter cubed and the temperature is 37 degrees Celsius, what is the pressure? Well, here we just need to employ the gas law, PV equals nRT, where the pressure is what we don't know, so that equals nRT divided by V, the volume, and now we just substitute in the number of moles we just calculated is 1.14, that's N. R is the gas constant, 8.31. T is the temperature, of course, in degrees Kelvin, so it was 37, so you have to add that to 273 to get 310, divided by the volume, which we were told was 0.02 meter cubed. And if you put that in the calculator, you should find that the pressure comes out at 146,837 pascals. Question 2. We have a helium balloon whose volume at ground level is 15 cubic meters. The temperature is 300 degrees K and the pressure is 1 times 10 to the 5th Pascal. When it gets to a height, it has a volume of 30 cubic meters and the temperature is 250 K. What is the pressure when it reaches that height? Well, we're now going to take the idea that P1 V1 over T1 equals P2 V2 over T2. That is to say that the pressure, volume and temperature at one position will equal the pressure, volume and temperature, or rather the pressure, volume divided by the temperature at the second position. So now what we don't know is the pressure at height, which we'll call P2. So P2 is going to be P1 V1 over T1 times T2 over V2. And we're told that P1 is 1 times 10 to the 5th. V1 is 15 meter cubed. And T1 was 300 K. And then at height, T2 we're told is 250 K, and V2 was 30 cubic meters. And if you put that into a calculator, I think you'll find that P2 is equal to 41666 Pascal. So a dramatic reduction in pressure. Question 3. The mass of 1 mole of nitrogen is 2.8 times 10 to the minus 2 kilograms. We had that in question 1. We're asked 2 questions. What is the mass of 1 molecule? And what is the typical or average speed of that molecule at 300 Kelvin? Well, we know that the mass of 1 mole is 2.8 times 10 to the minus 2 kilograms. And we know how many molecules there are in a mole because that is the Avogadro constant, 6.02 times 10 to the 23. So if we divide one by the other, the mass of a mole divided by the number of molecules in a mole, we will get the mass of a molecule, which comes out to 4.65 times 10 to the minus 26 kilograms. And now we're asked to find the typical or average speed of that molecule. So it's a molecule of a gas. So here we'll need the formulae that half mv squared, which is the kinetic energy, is also the same as 3 over 2 kT. It's the 3 over 2 kT formula we need here, not the E equals kT formula, because here we're talking about kinetic energy from which we're going to derive velocity, kinetic energy of a particle of a gas. V is the average velocity, so V squared is going to be 3 kT divided by m, because the 2's cancel out, and that equals 3 times K, which is 1.38 times 10 to the minus 23, times the temperature, which was 300 Kelvin, divided by the mass of the molecule, which we just calculated. It was 4.65 times 10 to the minus 26. And if you put that through your calculator and then take the square root, because we've calculated V squared, you'll find that V is 517 meters per second. Question 4. A 3 kilogram metal cylinder is heated from 5 degrees to 15 degrees Celsius in 3 minutes. We use a heater which is rated as 12 volts and 6 amps. And the question is, what is the specific heat of the metal? Well, we know that the power of the heater, which we'll call P, is equal to VI, and that's going to be equal to 12 times 6, 12 volts, 6 amps, and that of course comes to 72 watts. And that can also of course be written as joules per second. A watt is a joule per second. So in 180 seconds, which is the 3 minutes we're asked about, the total energy supplied by that heater is going to be 72 joules per second times 180 seconds. I won't calculate that just yet. That energy is going towards raising the temperature of the metal. And the energy required to raise the temperature of the metal will be mass times specific heat times the change in temperature. So this energy provides that energy. So now we can write that 72 times 180, which is the number of joules that goes in 3 minutes, 180 seconds, is going to equal the mass, which was a 3 kilogram mass, times the specific heat, which we don't know, times the change in temperature. Well, it went from 5 to 15, so that's a change of 10 degrees. And if you multiply that out, you should get that the specific heat is equal to 432 joules per kilogram per degree Kelvin, or per degree centigrade, as you wish. Incidentally, I don't think it's too serious to talk about degrees Kelvin, though technically the term is just Kelvin. We talk of degrees centigrade, but just Kelvin. Every so often I lapse into degrees Kelvin. Sorry about that. Question 5. We have a 3 kilowatt kettle. It has 1 kilogram of water, and that water is already at boiling point. And the question is, how long will it take for the kettle to boil dry? We're given that the specific heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. Well, the energy to vaporize that water will equal the mass times the specific heat. The mass was 1 kilogram, and the specific heat we were given is 2.26 times 10 to the 6. And that's going to give you the energy in joules. The kettle is providing 3 kilowatts, which means it's providing 3,000 joules per second. So consequently, the time taken will be the energy required, which is 2.26 times 10 to the 6, divided by the energy provided per second, which is 3 times 10 to the 3. And that comes out to 753 seconds. Question 6. 80 joules of work is done to a system which loses 30 joules in heat. What is the effect on its internal energy? Well, essentially we've got a system and we put 80 joules of work in and we lose 30 joules out. And we're obviously going to use the first law of thermodynamics, delta U equals delta Q plus delta W. All of those means that delta U means an increase in energy, delta Q means heat in, and delta W means work in. So now we've got that delta U is equal to delta Q. Well, we haven't got heat in, we've got heat out, so that's minus 30 joules. But we have got work in, so that's plus 80, and that gives you plus 50 joules. So consequently, the internal energy will increase by 50 joules. The second question is, what will happen to temperature? Will it go up or down? Well, the internal energy increases by 50 joules. Internal energy is a function of temperature. If the internal energy goes up, the temperature goes up. Question 7. We have a tank of water at 300 K. First question, what is the average energy of a water molecule? Well, here we're going to use the formula that E equals KT. We're not talking about a gas now, we're talking about thermal energy of a water molecule, E equals KT, and that's simply going to be 1.38 times 10 to the minus 23, which is Boltzmann's constant K, times the temperature in Kelvin, which is 300, and that will give you 4.1 times 10 to the minus 21, 10 to the minus 21 joules. That's the average energy of a water molecule. The second part of the question, water, which is H2O, has 2 hydrogen bonds. The energy to break each bond is 3.2 times 10 to the minus 20 joules. So what is the energy required for the molecule to evaporate? Well, the assumption here is that if the bonds break, the water evaporates, and so you're going to need 3.2 times 10 to the minus 20 joules for each bond, so you're going to need a total energy to break the 2 bonds of 2 times 3.2 times 10 to the minus 20 joules, which of course is equal to 6.4 times 10 to the minus 20 joules. The third part of the question is, what is epsilon over kT, which of course is a function used in the Boltzmann formulae. So we're asked, what is epsilon over kT? Well, epsilon is the activation energy, and we were given that. That's now 6.4 times 10 to the minus 20, because we were given that the energy to break one bond is 3.2 times 10 to the minus 20, but we've got to break 2 bonds, so we need an activation energy of 6.4. Divide that by kT. Well, we calculated kT, up here. That's 4.1 times 10 to the minus 21. And that comes out to approximately 15. And what you should recognise from that is that although the average energy, which is kT, is only 1/15 of that required for the activation energy, there will be some molecules that will have the energy kT, because remember, the energy of molecules is in a distribution, the average of which is kT. But at the far end of that distribution there will be energies, but they will only be held by a very small proportion of the molecules. Nonetheless, some will have enough energy to break the bonds and evaporate. So the fourth part of the question is, what will the impact be on the water in the tank? And the answer is that since epsilon over kT is about 15, which is somewhere between 15 and 30, is usually the number we take to say there will be a substantial amount of activation, because there are enough molecules with the activation energy. That means some of that water will evaporate. Not all of it, of course. So some will evaporate, and that means you'll need to keep topping up the tank because the water level will go down. Question 8. We have 200 grams of ice at minus 15 degrees Celsius. We have a heater that is capable of supplying 100 joules per second, that's 100 watts, and after 63 seconds all the ice has reached 0 degrees Celsius. And the first question is, what is the specific heat of the ice? Well, we will remember that we need to use the formula that the energy required to raise the temperature is equal to the mass times the specific heat times the change in temperature. Specific heat is what we don't know, that's what we're trying to find. We know that it took 63 seconds and that the heater is providing 100 joules per second, so the total energy supplied will be 100 joules times 63 seconds, and that's going to be equal to the mass, which is 200 grams or 0.2 kilograms, times the specific heat we don't know, times the change in temperature, which was from minus 15 to 0, and that is minus 15. 15 degrees goes from minus 15 to 0. We have not changed state. The ice is still ice at 0 degrees, so we haven't got to worry about specific heat of melting. Well, from this you can see that the specific heat is going to equal 100 times 63 divided by 0.2 times 15, and that comes to 2100 joules per kilogram per Kelvin or degree Celsius, as you wish. And the second part of the question is, what will the temperature be after a further 20 minutes? We're given two important pieces of information. Firstly, the specific heat of water is 4,200 joules per kilogram per Kelvin, and the latent heat of fusion from ice to water, or latent heat of melting, is 3.3 times 10 to the 5 joules per kilogram. Well, firstly we want to know how much energy is going to be supplied by the heater. The heater supplies 100 joules per second, and we're told that this is 20 minutes, so that's going to be that the total energy supplied by the heater will be 100 joules per second times 20 minutes expressed in seconds is 1200 seconds, and that's going to come to 120,000 joules. And that energy has got to do two things. Firstly, it's got to melt the ice, which is at 0 degrees, and then it's got to raise the now water through a temperature delta T. So firstly, to melt the ice, we need the mass, which is 0.2, times the specific heat of fusion, which was 3.3 times 10 to the 5th, and that will simply take ice at 0 degrees and convert it to water at 0 degrees. And then to raise the temperature still further, we need mass, 0.2, times the specific heat, which we were given as 4,200, times the change in temperature, which we don't know. So this amount of energy provided by the heater is going to be the energy required to melt the ice, plus the energy required to raise the temperature of the now water through delta T. And if you simply substitute well, if you simply rearrange the formula actually, you should be able to calculate for yourself that delta T is 64.3 degrees. So after 20 minutes, if the heater continues to provide heat, and assuming of course 100% efficiency and no heat loss, then the water will be at 64.3 degrees. Question 9. We have a fixed mass of gas at a low temperature which is in a container where the volume can change but the pressure will remain constant. The pressure is 1 times 10 to the 5th Pascal, and the temperature is 0 degrees Celsius, and the volume is 3 times 10 to the minus 3 meter cubed. The first question we're asked is, what is the number of moles of gas? Well, for that we simply need that PV equals nRT, where n is the number of moles, what we want, and R of course is the gas constant, but that means that n is equal to PV divided by RT. The pressure we were told was 10 to the 5th, the volume was 3 times 10 to the minus 3, R will normally be given 8.31 times the temperature, which in Kelvin is 273, it was 0 degrees Celsius. And that comes to N equals 0.132 moles, not molecules, moles. Part 2 of the question, what is the average kinetic energy at 40 degrees Celsius of a molecule? Well, we're talking about a molecule in a gas and we're talking about kinetic energy, so we're going to need the formula that Ke is equal to 3 over 2 kT. This is not thermal energy, this is kinetic energy, so it's not E equals kT, it's E equals 3 over 2 kT, and that's simply going to be 3 over 2 times the Boltzmann constant, which is 1.38 times 10 to the minus 23, a bit clearer, that's 10 to the minus 23, times the temperature, which at 40 degrees will be 313 Kelvin. And if you multiply that through, you should get that the kinetic energy per molecule, the average kinetic energy of a molecule, 648 times 10 to the minus 23 joules. Remember, that's the average kinetic energy of a molecule. The molecules will have a wide range, a statistical distribution of energies, but the average will be 648 times 10 to the minus 23 joules. And the third part of the question is, what is the total internal energy of the gas? Well, we know what the energy of one molecule is, we just calculated that, so the total energy will be the energy of a molecule multiplied by the number of molecules. So total energy will be 648 times 10 to the minus 23 times the number of molecules. Well, we don't know what that is, but we did calculate the number of moles. So if we multiply by 0.132, we've got the number of moles, and you multiply by Avogadro's number to get the number of molecules. 6.02 times 10 to the 23, and that will give you 515 joules. Sorry, 515 joules. So the total internal energy of the gas is 515 joules. Question 10, we have a bicycle tyre. The volume of the gas in the bicycle tyre is 2 times 10 to the minus 3 cubic metres. The pressure of that gas is 3.5 times 10 to the 5th Pascal. The temperature is 290 K. First part of the question, what is the number of moles of gas, we'll assume it's air, in the bicycle tyre? For that we'll need the formula that PV equals nRT. We're going to assume throughout that this gas behaves like an ideal gas, and so we've got that N is equal to PV divided by RT, which equals the pressure, 3.5 times 10 to the 5th, times the volume, 2 times 10 to the minus 3, divided by R, which is usually given, it's 8.31, times the temperature, which is 290, and if you multiply that through, you should find that the number of moles is 0.2905 moles, not molecules, moles. Part 2 of the question, if the temperature is increased to 300 K, what will the pressure be? Well, we can use the formula that P1 V1 over T1 is equal to P2 V2 over T2, but because it's a bicycle tyre, the volume is not going to change, so we can regard the volumes as being the same, V1 equals V2, so they cancel out. And now we get that P2, which we don't know, is equal to P1 T2 divided by T1. So that means that P2 is going to be equal to P1, which of course was 3.5 times 10 to the 5th, times T2, which is now 300 K, divided by T1, which was 290 K, and that will give you a pressure equal to 3.62 times 10 to the 5 Pascal. So the pressure has gone up, and that's entirely consistent with this formula here. Volume is now a constant because it's unchanging. N and R are constants, so pressure is directly proportional to temperature. If the temperature goes up, the pressure must go up. If you are asked to find the average kinetic energy or velocity of a molecule in a gas, then you'll use the kinetic energy equals 3 over 2 kT. If, on the other hand, you're asked to find the average thermal energy of, say, a molecule in water, then you'll use E equals kT. E equals kT is not precise, but it is near enough. Next, there are two equations to do with specific heat. If you take a mass of a substance and you raise it through several degrees Kelvin or centigrade, then the energy required to raise the temperature will be the mass of material multiplied by its specific heat multiplied. Hello, today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on thermal physics. First, let's just work through the formulae and other information that you're likely to need. The ideal gas law, PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the molar gas constant, and T is the temperature. Bearing in mind very few gases are ideal gases, but some at least behave close to an ideal gas to enable us to use the formulae. R, the molar gas constant, has a value of 8.31 joules per mole per Kelvin. The Avogadro are hitting the walls of a cube, a theoretical cube, and you calculate the pressure, which results from the force over the area, and from that you can work out that the average kinetic energy, which is associated with the average velocity, is 3 over 2 kT. The formula E equals kT is a measure of thermal energy. The previous one was kinetic energy. Now, they are not exclusive, of course. Kinetic energy can include thermal energy and vice versa, but this is specifically a thermal energy measure. It is the average thermal energy of a particle in a system, and it is derived from the Boltzmann statistical distribution. So Avogadro number, or Avogadro constant, is 6.02 times 10 to the 23 molecules per mole. So in any mole of a substance, there will be 6.02 times 10 to the 23 molecules. Kinetic energy of a gas, which of course we could typically write as a half mv squared, where v in this case is the average velocity of the molecules in a gas, given that they will all be travelling at different velocities. But if v is the average velocity, then that equates to 3 over 2 times kT, where k is the Boltzmann constant and T is the temperature. The value of k is 1.38 times 10 to the minus 23 joules per molecule per Kelvin. And that means that the gas constant, R, is equal to the Avogadro constant times the Boltzmann constant. Then we come to the formula E equals kT. Now it's here that people often ask me, what is the difference between E equals kT and E equals 3 over 2 kT? Well, in the case of E equals 3 over 2 kT, This is a formula that is derived from the ideal gas law, and considering molecules moving about in all directions, you work out what proportion